Compilers are one of the most overcomplicated pieces of software in existence for something as simple as they are. The majority describe compilers by their implementation rather than their goal, and I think that's why people find compilers to be so complicated. In reality, a compiler is just a program that reads bytes from a file and writes different bytes to a new file based on the content of the input file. That's it, just a translation from A to B. The way you implement a compiler is entirely up to you. Over time, people have developed standard methods and algorithms, but at its core, it's all about taking one format of data and turning it into another. Transpilers are the simplest form of compilers. They translate one high-level language to another high-level language. Prominent examples include TypeScript, which transpiles to JavaScript, CoffeeScript, which transpiles to JavaScript, Elm, which transpiles to JavaScript, Scala, which transpiles to JavaScript and Java, bytecode, and even Svelte, which compiles its syntax to plain vanilla JavaScript. The terms transpile and compile can kind of be used interchangeably because transpilation is really just a more specific type of compilation. Now, many will disagree with me here, but I would even go as far as to argue that assemblers are a type of compiler. Many assemblers have their own syntax and directives, making them no different than regular compilers. Assemblers translate human-readable representations of machine code to actual machine code. In my opinion, they still fit the original definition of a compiler. Java is also a compiler that translates its high-level source code into its own bytecode format. This bytecode format is later ingested by its virtual machine, which mimics the behavior of a regular processor. I also don't really think it matters what direction you go in. Ghidra's disassembler and decompiler are still valid compilers in my book because they're still a translation from bytes to bytes. They instead just translate machine code back into human-readable assembly or higher-level code. It's still just a translation, but in reverse. But enough yapping, it's time for me to actually show you some code so you understand how minimalistic a compiler can really be. So this program just translates some pseudocode into a C program. It's in Odin, my favorite language. Now, while some people would probably argue that this is not even a valid compiler, it still does what a compiler essentially does. This program reads a file, parses a statement like print and hello, and writes a simple C program to a new file. And while it's basic, even to the point of being able to question whether or not this can even be considered a valid compiler, it still demonstrates how a compiler could translate text into code from another language. Machine code isn't magic. In fact, machine code is more rigid than high-level code. So in a way, it's simpler, just not exactly human readable. It's just a binary format for a specific platform and architecture. If the platform is Windows and the architecture is x86, you might write bytes for a 32-bit portable executable. If the architecture is x64, then you might write bytes for a 64-bit portable executable. And if the platform is Linux, then you might write the bytes for an ELF format. I assume you can kind of get the pattern that I'm making. Literally just architecture, platform. Also, computers and processors, same thing basically, are just big, giant state machines. They read each instruction as a sequence of opcodes, and then behave in a certain way depending on the opcode. This behavior is based off of the voltage states of billions of transistors built from microscopic silicon semiconductors as a result of insane feats of electrical engineering. Opcodes are the actual numeric values behind instructions that would be included and visible in the machine code. Registers are also encoded as numbers as well. But the point is, as long as you know the underlying platform and architecture and the binary format, producing the machine code is relatively straightforward, mostly just time consuming. Producing machine code for several different platforms and producing optimized machine code is a completely different story. I would also like to briefly talk about interpreters since they're usually brought up when discussing this topic. Interpreters are essentially just programs that run code. They simulate the behavior of a compiled program and share many similarities with virtual machines. A virtual machine might read a sequence of bytes and then behave differently depending on the bytes, while an interpreter does the exact same thing. It's just that instead of bytecode, it's a high-level language, which is a lot more complicated and slow of a process. Another thing of note is that virtual machines also mimic hardware in that they have, in a way, their own instruction set, and their behavior is predictable based on each byte in the bytecode, similar to opcodes. And you could target a bytecode format similar to how you would a real machine, while you wouldn't really do this for interpreted languages. The prominent examples of interpreters include Python, Lua, and JavaScript. But Java could also be considered both a compiler and interpreter. It compiles to bytecode and interprets its own bytecode using the JVM. Therefore, it's considered a bytecode interpreter. I should clarify that the Java compiler and the Java virtual machine are separate entities. How you interpret code is up to you. The simplest form is by using a tree walking interpreter. It simply simulates the behavior internally in the implementation language by traversing the nodes of the AST. But in reality, the most common form of interpretation in modern day is JIT compilation, or just-in-time compilation. It compiles a portion of the program just before execution. And this can really be better described as creating and executing executable code that wasn't part of the program on disk. While this almost always leads to faster execution than direct interpretation during runtime, it's usually slower in the context of an already running interpreter that has to take on the overhead of compiling right before execution. This hopefully gives you a better idea of how compilers work, and maybe interpreters too, and perhaps we can go over implementing a simple one in the future. Anyways, hope you learned something.